2 billion miles from the Sun, orbiting a planet tipped over onto its side, there is a moon that looks broken. Not cratered, not scarred, broken. As if someone shattered it into mismatched pieces and pressed them back together by hand. Ancient plains sit beside enormous grooved ovals. Cliffs plunge for miles into the dark. Canyons cut deeper than anything on Earth. And Miranda is barely 300 miles wide. Far too small to still be alive inside. A world this tiny should be a frozen, quiet ball of ice. Instead, Voyager 2 found a surface stitched together from several different worlds and several different ages. For nearly 40 years, that has haunted the scientists who study it. So what tore Miranda apart, and what exactly put it back together? If you enjoy getting lost in the strangest corners of the solar system, it would mean a lot if you tapped the like button and subscribed. It quietly helps these long deep dives reach more curious people, like you. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, are you comfortable? Let's begin. For 8.5 years, a machine the size of a small car fell through the dark toward a planet almost nobody was paying attention to. It had already done the impossible. Launched from Florida on the 20th of August 1977, the spacecraft called Voyager 2 had ridden a once-in-176-year alignment of the outer worlds, using the gravity of one giant planet to slingshot it toward the next. Jupiter had flung it onward to Saturn. Saturn had bent its path toward a target so distant that when the mission was first drawn up, no one was even certain the aging probe would survive long enough to reach it. But it did survive. And in January of 1986, Voyager 2 became the first, and to this day, the only spacecraft humanity has ever sent to the 7th planet from the Sun. The engineers back at the Jet Propulsion Laboratory in California were nervous, and they had reason to be. The spacecraft was now so far away that its radio whispers, traveling at the speed of light, took nearly 3 hours just to reach Earth. Everything Voyager 2 did during its brief encounter, it would have to do alone, on instructions written and uploaded weeks in advance. There would be no second attempt. The probe was moving far too fast and the planet was far too remote. Whatever it saw in those few hours, it would see once, and then it would fly on into the blackness forever. And the world it was approaching was one of the strangest in the entire solar system. Uranus is a planet that breaks the pattern of everything around it. It was discovered by accident on the 13th of March, 1781, by a musician turned astronomer named William Herschel, who at first thought he had found a comet. When the truth sank in, it doubled the known size of the solar system overnight, because Uranus sits at a staggering distance from the Sun, nearly 2 billion miles out, so remote that a single one of its years lasts about 84 of ours. Sunlight that reaches it is dim and thin. Noon on Uranus is dimmer than deep twilight on Earth. It is a cold, blue-green world of hydrogen, helium, water, ammonia, and methane, and for 2 centuries it was little more than a faint dot in a telescope. But the truly bizarre thing about Uranus is not its distance. It is the way it lies down. Every other major planet spins more or less upright as it circles the Sun, tilted a little the way Earth's tilted, which is what gives us our gentle seasons. Uranus does not do this. Uranus is tipped over by roughly 98 degrees. It is knocked completely onto its side, so that its poles, not its equator, take turns pointing almost straight at the distant Sun. Scientists believe that early in its history, some enormous body, Perhaps an ancient world several times the mass of Earth slammed into Uranus and toppled it. Whatever the cause, the result is a planet that rolls around its orbit like a ball rolling on its side rather than the top spinning upright. That single fact reshapes everything about the Uranian system. Because the planet is on its side, its seasons are monstrous. Each pole is bathed in about 42 years of unbroken sunlight, and then plunged into about 42 years of unbroken darkness. And here is the part that matters most for our story. The moons of Uranus do not orbit around the planet's waistline the way our moon orbits Earth. They orbit around its tilted equator, which means the entire family of moons is tipped over with it. When Voyager 2 arrived in 1986, it did not approach a neat, flat system it could sail through, hopping from moon to moon the way it had at Jupiter and Saturn. It approached a system standing on end, the planet and its moons arranged in rings facing the incoming probe like a target seen head-on. This is why Voyager 2 got only one real chance at the moons of Uranus. It could not loop lazily around the system for months. It had to plunge straight through the bullseye in a single afternoon, and whatever moons happened to be near its path in that narrow window were the moons it would study. As the geometry worked out, the spacecraft's flight path carried it closer to the innermost of the large moons than to any other. That moon was the smallest of the family, the one scientists expected the least from, a frozen little runt that had barely earned a footnote in the mission plans. Its name was Miranda. Miranda had been discovered less than 40 years earlier, in 1948, by the Dutch-American astronomer Gerard Kuiper using a telescope in Texas. By then, 4 larger moons of Uranus were already known, and they had been given names drawn not from mythology, like most moons, but from English literature, chiefly the plays of William Shakespeare. So the newest and faintest of them was named Miranda, after the young heroine of Shakespeare's play, The Tempest, a girl who has grown up alone on a remote island and who, on seeing other people for the first time, cries out in wonder at the strange new world before her. It would turn out to be a fittingly ironic name, though nobody knew that yet. For decades after its discovery, Miranda was nothing but a speck. Even in the best telescopes on Earth, it was a single dim point of light, far too small and far too distant to show any detail at all. Astronomers could measure roughly how bright it was, and roughly how it moved, and from that they could estimate its size. And the size they arrived at was tiny. Miranda is only about 470 kilometers across. To put that in human terms, it is only about 1/7 as wide as the moon that hangs over your own backyard. You could set Miranda down on Earth and it would not span the distance between many neighboring cities. It is a small, cold ball of ice and rock, adrift in the dark, whipping around its giant parent planet once every 34 hours or so, close enough to Uranus that the planet would loom enormous in its black sky. And that is exactly why nobody expected anything from it. Here is the logic that every planetary scientist carried in their head as Voyager 2 closed in. To have an interesting surface, a world needs to be geologically active, or to have been active at some point in its past. It needs heat. Heat is what drives the churning, cracking, melting, and reshaping that gives a world mountains and valleys and fresh terrain. A dead, cold world does nothing. It simply sits there and collects impact craters, one after another for billions of years, until its surface is nothing but a monotonous field of overlapping scars. The moon we see from Earth is mostly like this across its ancient highlands. So is the planet Mercury. So are countless small icy bodies in the outer solar system. No heat, no activity, no story. Just craters on craters on craters. Now, where does a small world get heat from in the first place? There are really only two common sources. The first is heat left over from its violent birth, the warmth of a body still cooling from the era when it formed. The second is radioactivity, the slow trickle of energy released as unstable elements buried inside the rock decay over billions of years. Both of these sources have the same fatal weakness when it comes to a world like Miranda. They depend on volume, on how much material a body has stuffed inside it. But a world loses its heat through its surface, radiating it away into the cold of space. And this is the trap that small worlds fall into. As a body gets smaller, its volume shrinks much faster than its surface area does. A small world, therefore, has very little heat locked inside it, and a relatively enormous surface through which to lose that heat. It is like the difference between a great cauldron of soup and a single spoonful. The cauldron stays warm for hours. The spoonful goes cold almost the moment you lift it from the pot. Small worlds are the spoonful. They bleed their warmth away quickly and early, and then they freeze solid all the way through and stay that way for the rest of time. Miranda, by this reasoning, should have been the deadest of the dead. It is one of the smallest round bodies in the solar system. It sits nearly 2 billion miles from the only star that could warm it. In a region where the surface temperature hovers around a ferocious minus 210 degrees Celsius, cold enough that water ice is not a soft, workable material, but a rock as hard and brittle as granite. A world this small, this cold, and this old should have used up whatever heat it ever had within the first few 100 million years of its existence, and then gone utterly quiet. It should be a battered, ancient snowball, its entire surface uniformly cratered, geologically finished, telling one simple story and nothing more. That was the confident expectation. The scientists were not being lazy or careless. They were applying sound physics that works beautifully across most of the solar system. Every small icy moon they'd ever seen up close reinforced it. When Voyager 2 had swept past the little moons of Saturn a few years earlier, some of them had indeed shown surprising features, and that had already begun to unsettle a few researchers. But Miranda was smaller and colder and further out than almost anything, and most of the mission team fully expected it to be the boring one, the throwaway target, the frozen footnote they would photograph out of thoroughness before moving on to the real prizes. So the plan was almost casual. As Voyager 2 threaded through the tilted Uranian system on the 24th of January 1986, the trajectory that would bend the probe onward toward its next destination happened to carry it very close to Miranda. Closest approach to the little moon would be only about 29,000 kilometers. Closer than the spacecraft would come to any other moon in the system, close enough to see real detail. The cameras were commanded to turn and stare. Nobody at the Jet Propulsion Laboratory was expecting the images that came back to change anything. They expected craters. They expected a grey, dead, unremarkable world. They expected to nod, file the pictures, and move on. But nervousness alone does not capture the size of the technical problem the engineers faced. Because everything about Uranus conspired against a clear photograph. The first enemy was darkness. This far from the sun, sunlight is feeble. Uranus receives only about 1/400th of the light that falls on Earth, and even compared to the spacecraft's previous stop at Saturn, the light levels at Uranus were only about a quarter as strong. To capture anything in that gloom, Voyager 2's cameras needed long exposures, holding their shutters open for around 15 seconds at a time, simply to gather enough light to form an image, and that created the second enemy, motion. Voyager 2 was not drifting past its targets. It was tearing through the Uranian system at roughly 39,000 miles per hour. Holding a camera open for 15 seconds while moving that fast is a recipe for a smeared, useless blur. Imagine trying to photograph a dim room through the window of a car doing highway speed, with the shutter held open the whole time. Every frame would come back as a streak. To beat this, engineers on Earth reprogrammed the spacecraft's aging computers by radio, teaching it a trick called image motion compensation. During each long exposure, the spacecraft would slowly pivot under precise gyroscopic control, panning to track its target across the sky, so that the target stayed frozen in the frame even as Voyager 2 hurtled past it. The probe had to move in order to hold still. There were more enemies still. The cameras had been flying through space for more than 8 years, and their optics had collected flaws, specks and blobs of dust that the sharper new imaging only threatened to reveal. Worse, in the middle of January, only days before closest approach, a computer error began stamping intermittent light and dark streaks across some of the images. Engineers scrambled and corrected it in time, but it was a stark reminder of how many things could go wrong at the worst possible moment, with no chance to try again. Even a perfect photograph was only half the battle, because the picture still had to cross a vast, empty span of space to reach anyone. At that distance, Voyager 2's radio signal arriving at Earth was almost unimaginably faint. To catch it, NASA electronically linked its giant deep space network antennas together, combining several dishes to act as one enormous ear straining to hear a whisper from the edge of the planetary system. The encounter itself had been building for months. The formal approach began in November of 1985. But all of that preparation funneled down to a single, narrow window around closest approach, when the geometry would briefly place the moons within reach. It is worth pausing on how improvised all of this was. When Voyager 2 launched in 1977, reaching Uranus at all was not guaranteed. It was a hoped-for bonus, dependent on the spacecraft surviving far longer than its basic mission required. The probe that arrived in 1986 was therefore being asked to do things its designers had never fully planned for, running on computers with less memory than a modern greeting card that plays a tune, reprogrammed on the fly across a distance so vast that no correction from Earth could ever arrive quickly. Every capability that made the Miranda images possible, the long exposures, the panning, the signal combining on the ground, was a patch, a clever workaround layered onto hardware that had already been flying for the better part of a decade. And there was no dress rehearsal for the moons. Jupiter and Saturn had each offered the two Voyager craft multiple targets, and between them, several passes to learn from. Uranus offered one probe, one pass, one afternoon. Whatever close-up detail humanity was ever going to get of Miranda, Ariel, Umbriel, Titania, and Oberon, the first close-up detail anyone had ever obtained of any of them, had to be captured correctly the first time, in the dark, at speed, by a tired machine following instructions written weeks earlier. There would be no reviewing the results, and trying again tomorrow. Tomorrow, Uranus would already be shrinking in the rear view, and the spacecraft would be falling on toward Neptune and the emptiness beyond. For the moons, the timing was even more merciless than for the planet. Uranus is large and its features change slowly. A moon is small, and Voyager 2 would be alongside it for only minutes before the geometry slipped away. The commands to point the cameras, open the shutter for those long 15-second exposures, pan to compensate for the blistering closing speed, and then snap to the next target had to be choreographed to the second and loaded into the spacecraft in advance, blind, trusting that the machine would execute them flawlessly as it flew. When the sequence worked, it worked astonishingly well, resolving details on Miranda's surface down to roughly a kilometer across in the best frames. When you consider that these were the first close images of any Uranian moon ever taken, gathered in near total gloom by a probe moving faster than any human-made object had a right to be photographing anything, the wonder is not that the coverage was incomplete. The wonder is that it exists at all. For the scientists gathered at the Jet Propulsion Laboratory, there was also a quieter, heavier truth underneath the excitement. A mission like this comes once in a career, if that. Uranus is decades of travel away. Its seasons run longer than human lifetimes, and no follow-up was planned or funded. Many of the people in those rooms understood, on some level, that whatever Voyager 2 showed them of these moons in the next few hours might be all they would ever see of them. Not just for a while, but quite possibly for the rest of their lives. That is a strange pressure to carry into a single afternoon. It sharpened every image as it arrived, because each one was not merely data. It was, potentially, the only look humanity would get for a generation or more. Consider what those hours actually felt like. The spacecraft was hurtling through the system at tens of thousands of kilometers per hour. Everything was automated, because the light speed delay made real-time control impossible. On Earth, the scientists could do nothing but wait for the data to crawl across nearly 2 billion miles of space, arriving a full 3 hours after the fact. The encounter with the whole Uranian system lasted only about 6 hours of truly close observation, the payoff of a journey that had already taken 8.5 years. 6 hours. After all that time and all that distance, the heart of the mission came down to a single afternoon, and the moon in the closest seat happened to be the one nobody cared about. The signals began to arrive. Line by line, the images assembled themselves on the screens back on Earth, painted slowly out of the faint radio hiss returning from the edge of the known solar system. And as the picture of Miranda came into focus, the room did not react the way anyone had rehearsed. Because Miranda was wrong. It was wrong in a way that took a moment to even register, because the mind kept trying to force it into a familiar shape. This was supposed to be a simple, cratered ball. Instead, the surface that emerged looked less like a natural moon and more like something that had been taken apart and put back together by a careless hand. There were regions of old, battered, cratered ground, exactly as predicted, but they did not cover the whole moon. They ended. They stopped along sharp, startling boundaries, and beyond those boundaries lay terrain that looked nothing like them at all. Vast provinces of grooved and ridged material sat pressed up against the ancient plains, as though someone had cut a piece from one world and welded it onto another. Enormous scarps and fractures slashed across the surface. There were cliffs that seemed to fall away for miles into shadow. There were strange, sharp-edged, geometric shapes, Huge regions with crisp outlines that no natural weathering process should have left behind on a dead moon. Nothing about it made sense. A world this small was not supposed to be able to do any of this. It had no business having young terrain and old terrain side by side, because young terrain means resurfacing, and resurfacing means heat, and heat was precisely the thing Miranda was not supposed to possess. And yet, here it was, a patchwork, a mismatch, a face that looked assembled from spare parts belonging to several different worlds and several different ages, all crammed onto a single frozen ball, smaller than many countries on Earth. The scientists in that room were among the most experienced planetary geologists alive. They'd studied the Moon, Mars, Mercury, and the moons of Jupiter and Saturn. They knew what natural surfaces looked like. And when they looked at Miranda, several of them said, in one form or another, the same thing. This looks like it was broken and rebuilt. Not because they believed a moon had literally been shattered and glued back together, but because that was the only phrase that captured the sheer visual violence of the mismatch. The word that would follow Miranda for the next 4 decades was not cratered or ancient. It was something closer to unexplainable. And the cruelty of the encounter was that they were seeing only part of it. Because Uranus lies on its side, and because the whole system was facing Voyager 2 like a target, the sun was shining almost straight down on the southern half of Miranda, while the northern half lay in total darkness. Voyager 2 could photograph only the lit portion, and only from the angles its single fast pass allowed. Roughly half of Miranda's surface was never seen in any detail at all. It rolled beneath a spacecraft draped in a decades-long polar night, and there it has remained, unseen, ever since. Whatever the little moon was hiding on its far side, it kept. So in the span of a single afternoon, the throwaway target, the afterthought, the boring footnote, became the most bewildering object of the entire Voyager mission to Uranus. The physics had been so clear. Small world, ancient world, cold world, dead world, and Miranda had ignored all of it. It had somehow reached across billions of years and produced a surface so violent, so contradictory, so stitched together that the people who had spent their careers explaining how worlds behave found themselves staring at a picture they could not explain. They had gone looking for craters. They had found something that looked as though it had been taken apart at the seams. And now the real question, the one that would outlive the mission itself and drive scientists to argue for the next 40 years, was only beginning to form. What exactly were they looking at? To understand why Miranda unsettled the scientists so deeply, you have to understand what a planetary geologist actually does when a new world appears on the screen. They read it. A surface is a record, a document written in stone and ice, and every feature on it is a sentence in a story about what happened and when. A crater is one kind of sentence. A ridge is another. A crack, a cliff, a smooth plain, a jagged scarp. Each one is a clue about the forces that shaped the ground and the order in which they acted. Give a trained eye a clear picture of any world, and that eye can begin to reconstruct its history, sometimes going back billions of years. So when the images of Miranda finished assembling themselves back at the Jet Propulsion Laboratory in 1986, the geologists did what they always do. They began to read. And almost immediately the sentences stopped making sense together. Because Miranda was not telling one story. It was telling several, and they did not belong on the same world. start with the part that behaved. Across some regions of Miranda, the ground looked exactly the way the pre-flyby predictions had insisted the whole moon would look. It was old, rolling, and heavily cratered, pocked by impact after impact, a gently undulating landscape of overlapping scars. This is the signature of ancient dead terrain, and reading it is a bit like counting tally marks scratched onto a wall. Craters accumulate slowly and steadily over enormous spans of time, as debris rains down from space. The more craters a patch of ground carries, the longer it has sat there undisturbed, exposed to the sky. A surface crowded with them is a surface that has done nothing for billions of years, quietly collecting hits like marks on a very old clock. On Miranda, these cratered plains were the moon the scientists had come expecting to find. Frozen, finished, simple. But those plains did not cover the moon. They stopped. And the way they stopped was the first thing that made the room go quiet. Ancient cratered ground on a normal world does not end at a hard line. It fades, it merges, it grades gently into whatever lies beside it. On Miranda, the old terrain ran headlong into something completely different and simply halted, cut off along sharp, startling borders as if someone had taken a knife to the map. On the far side of those borders lay terrain that carried almost no craters at all. And terrain with few craters is, by the same tallymark logic, young terrain. It has not been sitting exposed for billions of years, because something happened to it more recently. Something that wiped the old craters away and reset the clock. Something resurfaced it. This was the contradiction, stated in its simplest form. On one small frozen moon, there was terrain so old it had collected the scars of the entire history of the solar system and pressed right up against it. Along knife-edge boundaries, there was terrain so young that its clock had been reset long after Miranda formed. Old and young, dead and reworked, side by side, on a world that was never supposed to have had the energy to rework anything at all. It was as though a geologist had been handed a single photograph and told it showed one place, and yet half the photograph was of an ancient ruin, and the other half was of a fresh construction site with no transition between them. And the young terrain was not merely smooth and blank. It was violent in its own right. Where the cratered plains were gentle and rolling, the reworked regions were slashed and grooved, carved into vast systems of parallel ridges and troughs that ran for tens of kilometers in tight, disciplined bands. There were fault scarps, immense cliff-like steps where whole slabs of the crust had shifted against one another. There were canyons of staggering depth, chasms cut into the ice that in places may plunge some 10 to 20 kilometers down, likely deeper than any canyon on Earth. There were grooves, running beside grooves, running beside grooves, curved and straight, some of them wrapping around in great sweeping arcs. This was not the quiet decay of a dead world. This was the fingerprint of tectonics, of a crust that had been stretched, cracked, pushed, and pulled with tremendous force. And every bit of that force was a problem, because force needs energy. And energy was the one thing a moon this small was not supposed to have. Then there was the cliff. Among the fault scarps that scar Miranda's young terrain, one stands out even in the limited, decades-old images we have, and it has since become the moon's single most famous feature. It is called Verona Rupes. Its name drawn, like everything on Miranda, from the world of William Shakespeare. Verona being the city of his star-crossed lovers, and Rupes being simply the Latin word planetary scientists use for a cliff or scarp. Verona Rupes is a colossal fault scarp, a place where the crust has broken and one side has dropped away from the other, leaving an enormous cliff face running for well over 100 kilometers across the surface. And it is tall. Precisely how tall is a genuinely open question, and it is worth being careful here because Verona Rupes is often described in breathless terms that outrun the actual evidence. Here is what can honestly be said. The estimates for the height of Verona Rupes range widely, from around 5 kilometers at the low end to as much as 20 kilometers at the high end. That is an enormous spread, and the reason for it is important. To feel what even the low end of that range means, picture the altitude at which passenger jets cruise, a little over 10 kilometers up, so high that the ground below fades to an abstract map, and the air outside is lethally thin. Now, stand the entire distance on its end as a single wall of ice and rock, and let it climb higher still toward the upper estimates. On Earth, the sheer face of Mount Everest from base to summit would not reach the top. There's nothing remotely like it on our planet. No cliff, no gorge wall, no mountain face that drops in one clean, uninterrupted plunge from a height where jetliners fly down to the frozen ground below. Everything we know about this cliff comes from a handful of images taken during a single, fast flyby, from tens of thousands of kilometers away, with the sun striking the surface at a low angle. Heights on a distant world are usually worked out from the shadows features cast, and shadow measurements from one brief pass, at one geometry, carry real uncertainty. So the popular claim that Verona Rupes is definitively the tallest cliff in the entire solar system should be softened. It is plausibly the tallest known cliff we have yet found anywhere. It may well hold that record, but the honest version keeps the word plausibly in the sentence, because our single glimpse of it is simply not precise enough to crown it with certainty. What is not in doubt is that the cliff is spectacular by any measure, and Miranda's feeble gravity makes it stranger still. Miranda is so small that its surface gravity is only about 8,000ths of Earth's. You would weigh less than a single % of your Earth weight standing on it. That has a bizarre consequence for a cliff this size. If you were foolish enough to step off the top of Verona Rupes, you would not plummet. You would fall the way a dropped coin drifts down through honey, gently accelerating in the near absence of gravity, taking something on the order of 10 to 12 minutes to reach the bottom. You would still arrive moving at a couple of 100 kilometers per hour, fast enough to be the last thing you ever did. But the fall itself would be a long, slow, almost dreamlike descent past a wall of ice miles high. It is the kind of place that sounds invented. It is entirely real, and we've seen it exactly once. And that phrase, seen it once, is the shadow hanging over everything in this part of the story. Remember that because Uranus lies on its side, the sun was pouring down on Miranda's southern half during the flyby, while the northern half lay in darkness. Voyager 2 photographed only what was lit, and only from the angles a single pass allowed. Verona Rupes, the canyons, the grooved provinces, the sharp borders, all of it comes from roughly half of one small moon, imaged in a hurry at modest resolution. The rest of Miranda has never been seen clearly at all. Whatever cliffs or chasms or contradictions wait on the unlit hemisphere, they waited then and they are waiting now. But the features that truly earned Miranda its reputation, the ones that made experienced scientists reach for the language of a broken and rebuilt world, were none of the things described so far. They were the coronae. A corona, in this context, is a large, roughly oval or trapezoidal region of the surface, filled with concentric and parallel bands of ridges and grooves, set off from the surrounding terrain by a sharp outer boundary. Miranda has 3 of them large enough to have been named, and their names, once again, come straight out of Shakespeare. Arden Corona, Elsinore Corona, and Inverness Corona, after the forest in one of his comedies, the castle in Hamlet, and the Scottish setting of Macbeth. Each is enormous relative to the moon that carries it, measuring up to roughly 300 kilometers across, which on a body only about 470 kilometers wide means a single corona can span a substantial fraction of an entire hemisphere. Together, these 3 vast provinces dominate the face of Miranda that we have seen. It is hard to overstate how strange they look. The cratered plains look natural, if ancient. The fault scarps and canyons look violent, but they at least look like the kind of cracking and shifting that stressed ground can produce. The coronae look designed. Their internal bands of ridges and troughs run in tight, ordered sets, sometimes concentric, sometimes sharply changing direction, and their outer edges are so crisp and so geometric that the eye insists they were drawn deliberately with a ruler and a compass, rather than shaped by any natural process. Inverness Corona is the most notorious of the 3. Near its heart sits a bright, pale feature in the unmistakable shape of a checkmark, or a letter placed cleanly on the dark surrounding surface, a geometric brightness so regular that it looks stenciled on. It is worth walking each of the 3 in turn, because although they share a family resemblance, they are not identical, and their differences carry real information. Inverness Corona is the smallest of the 3, and the one we can speak about with the most confidence. For a simple reason. It sits near Miranda's south pole, which means it fell squarely in the sunlit region during the flyby, and it is the only one of the corona that Voyager 2 managed to image in its entirety. It is roughly trapezoidal, and its interior is a crisp weave of ridges and grooves crossing one another, enclosed by sharp bounding faults. It also holds the bright geometric chevron already described, the pale checkmark that looks stenciled onto the dark surface. And by the crater counting logic laid out earlier, Inverness appears to be the youngest of Miranda's major terrains. Some estimates place its resurfacing within roughly the last few 100 million years, though the uncertainties on such figures are large. It is the most recently reworked of the 3. Arden Corona is the largest, a sprawling ovoid sitting on the leading side of Miranda, the hemisphere that faces forward as the moon travels along its orbit. Voyager 2 caught only part of it before the moon rotated its remainder into shadow, so we are quite literally missing pieces of the biggest single structure on the moon. What we can see is banded, laced with sets of parallel ridges and troughs that curve around the corona's margin like contour lines, drawn tightly around a hill on a map. Its outer boundary is one of the sharpest and most dramatic on Miranda, a place where the ordered banding of the corona meets the rougher, older ground beyond along a startlingly clean edge. Elsinore Corona sits opposite Arden, on the trailing side of the moon, the hemisphere that faces backward along the orbit. Like Arden, it was only partly imaged. It carries its own concentric fabric of ridges and troughs, but it is dusted with more craters than Inverness, and by that measure it appears to be the oldest of the 3 coronae, the most time-worn of them. The fact that Arden and Elsinore sit almost exactly on the leading and trailing faces of Miranda is not a throwaway detail either. It is a geometric hint that will matter greatly when we come to explain how these features formed, and it is exactly the sort of clue the rest of this story will turn on. Threading between and around all three coronae is something easy to overlook amid the drama of the great ovoids, but arguably just as important, a vast interconnected system of faults and rifts spreading across the whole southern hemisphere. Miranda is not simply a moon with three strange provinces sitting on otherwise quiet ground. Its entire visible face is fractured, cross-cut by a global network of cracks, grabens, and scarps, as though the moon had been pulled and strained until its shell split along countless lines at once, like a single sharp impact spreading a web of cracks across a windshield. Some of this faulting appears to predate the coronae, and some of it appears to come after, which tells us that Miranda did not deform in one tidy event. It expanded and cracked in more than one episode, before and after the corona themselves took shape. Step closer to the texture that fills the coronae and the young terrain, and you find it is remarkably orderly. Planetary geologists call it ridge and trough terrain, and the name is exactly what it sounds like. Long, roughly parallel ridges alternating with long, roughly parallel valleys, marching side by side in disciplined sets for tens of kilometers. Terrain like this is a signature. It is what a brittle crust does when it is pulled apart. The surface breaks along many parallel faults, some blocks dropping down to form the troughs while others stand higher as the ridges. Viewed that way, the grooved fabric of Miranda's coronae is not decoration. It is the frozen record of a shell that was stretched over and over until it fractured into these repeating bands. Every groove is a place where the crust gave way. There is also a sobering limit hidden in this tour, one that compounds everything said so far. Of Miranda's three great coronae, only one, Inverness, has ever been seen from edge to edge. The largest, Arden, and the oldest Elsinore remain half-glimpsed, their far portions never resolved, rotated away into the dark during the single pass that gave us everything we know. We are trying to solve a moon whose three most important features include two we have never fully seen. It is a little like being asked to describe three paintings when one hangs in full light and the other two are each half hidden behind a curtain that has not moved in almost 40 years. And that layering of ages is the crux of it. The heavily cratered plains may be older than 3 billion years. Some estimates push their oldest patches beyond 3.5 billion. The coronae, by contrast, generally appear to have formed within the most recent quarter or so of Miranda's history. So when the eye takes in a single frame of Miranda and sees old cratered ground abutting a fresh corona across a hard border, it is not looking at one landscape. It is looking across an unimaginable gulf of time, a place where terrain billions of years old meets terrain that was reworked only recently. The two eras press together on the surface of one small, frozen, and long-forgotten little moon. It is not one strange feature that unsettles the eye. It is that every feature seems to come from a different moment and a different process, set beside the rest. Now put yourself in the chair of a geologist in 1986, looking at this for the first time. You have three gigantic geometric provinces, each with its own distinct internal texture, each bounded by hard edges, all jammed together onto one tiny moon, alongside patches of ancient cratered plains and slashed by canyons and towering cliffs. Nothing grades into anything else. Everything meets at seams. It genuinely looks as though someone gathered pieces of several different worlds. A piece of old cratered moon here, a slab of grooved terrain there, 3 great ovoids of banded rock, and fitted them together into a single body, leaving the joins visible. It looks assembled. It looks, to use the word that has clung to Miranda ever since, rebuilt. This is exactly the impression this moon gives at first glance. And it is precisely here that we have to be careful, because that impression is a trap. The coronae are natural geological formations. They are not literally chunks of other objects bolted onto Miranda's surface. They are not the seams of a moon that was smashed and glued. They are terrain that formed in place, out of Miranda's own crust, through geological processes acting on this one body. The reason they look like inserted pieces is that whatever processes made them operated over sharply defined regions with sharp boundaries, producing textures that contrast violently with everything around them. The appearance of assembly is real. The assembly itself is not. And holding those two ideas at once, that the moon looks reconstructed, but was not literally reconstructed, is the entire intellectual challenge of Miranda. The coronae mattered so much to scientists for a very specific reason, and it comes back to those geometric boundaries. In geology, sharp, well-organized boundaries are demanding. A gentle, fuzzy transition can be produced by all sorts of slow, sloppy processes. But a crisp edge, a hard border where one texture stops and another begins, requires a mechanism that acts in a controlled, concentrated way over a limited region and then stops. The coronae are not smears. They are provinces with outlines. Whatever made them had to switch on inside a defined area, do its work, and switch off at the edge. That is a much harder thing to explain than random cracking, and it is why the coronae, rather than the cliffs or the canyons, became the central puzzle. Any theory that hoped to account for Miranda had to account for these 3 enormous, banded ovoids above all else. They are the beating heart of the mystery, and any explanation that cannot reproduce them fails, no matter how well it handles everything else. So what was the first explanation? What did scientists reach for when they looked at a moon that appeared to have been broken into pieces and put back together? They reached, quite naturally, for exactly that idea. In the years following the flyby, one of the earliest and most striking proposals to explain Miranda was the notion that the moon had, at some point in its distant past, been catastrophically shattered, struck so hard by some large impacting body that it was blasted apart into a cloud of fragments. Those fragments, still bound together by their mutual gravity, would not have flown off into space. Instead, they would have fallen back together, reaccreting into a single body once more. And in that violent reassembly, so the idea went, the pieces would have come back together imperfectly and incompletely, jumbling material of different kinds and different ages into a single moon. Denser, rockier fragments might have begun sinking back toward the center, while lighter, icier materials stayed nearer the surface, and this churning, partially sorted rubble pile would freeze into place before it could ever settle into a smooth, orderly world. The coronae, in some versions of this picture, were interpreted as the surface expressions of large blocks that had partly sunk during the chaos, the visible tops of dense chunks caught in the act of settling. It is easy to see why this idea was so attractive, and why it spread so quickly beyond the scientific community into popular retellings of Miranda. It matched the picture perfectly. If you actually take pieces of different worlds and slam them together into one, you would expect precisely what Miranda shows. Old terrain next to young terrain, sharp seams between mismatched provinces, a surface that looks like the aftermath of a collision, because it was the aftermath of a collision. The shattered and reassembled hypothesis took the single, most striking visual fact about Miranda, that it looks broken and rebuilt, and simply declared that this was because it had been broken and rebuilt. There is a deep satisfaction in an explanation that lets the appearance be the answer. And in the mid-1980s, with only a few hurried images to work from and no way to look closer, it was a reasonable, even compelling thing to propose. It is important to give this idea its due, because it is historically central to the Miranda story, and it appears in nearly every popular account of the moon to this day. It was not foolish. It was a serious scientific hypothesis, put forward by serious people, and it captured something true about the emotional impact of those first pictures. For a while, the shattered moon was the story of Miranda, the version that made it into books and documentaries. The reason the little moon earned its reputation as the world that was blown apart and stuck back together. But even in its heyday, the hypothesis strained under its own weight, and the strain came from the same place all of Miranda's troubles come from: its size and the energy budget that size allows. Shattering a moon is not a small thing. To break a body of ice and rock several hundred kilometers across into fragments requires an impact of tremendous violence, and an impact that violent, delivering that much energy, tends to disperse a small, weakly bound moon rather than politely breaking it into pieces that fall neatly back together. Getting the collision powerful enough to shatter Miranda, but gentle enough to let it reassemble, and doing it in a way that produces three great geometric coronaes, with crisp banded interiors rather than a formless heap of rubble, turns out to be an extraordinarily delicate thing to arrange. The more carefully researchers looked at what the coronae actually are, organized, bounded, internally structured provinces, the less they looked like the frozen chaos of a reassembled rubble pile, and the more they looked like something built by forces acting from within the moon, over time, in a controlled way. And that word, within, is where the whole story is about to turn. Because if the coronae were not stamped onto Miranda by a catastrophe from outside, if they were instead raised up out of the moon's own interior by its own internal machinery, then the shattered moon hypothesis, for all its appeal, is answering the wrong question. The real question stops being what hit Miranda hard enough to break it, and becomes something far more difficult and far more interesting. What could possibly have been happening inside this frozen little world? A world too small to hold its heat, too cold to keep its ice soft, too far from the sun to be warmed from outside, to crack its crust, raise its coronae, carve its canyons, and rework whole hemispheres of its surface. Not once, but seemingly in several separate episodes across its history. A dead moon cannot do that. Everything the physics said, everything laid out in the moment before the flyby, insisted that Miranda had to be a frozen, finished ball of ice with no engine left to run. And yet the surface in front of the scientists was the surface of a world that had run its engine hard, and perhaps run it more than once. Something had heated Miranda from the inside. Something had given a tiny, distant, frozen moon the energy to remake itself. The face of the moon proved it had happened. The only thing missing was any idea of how such a thing could be possible at all. The problem, stripped to its bones, was this. Miranda's surface was the surface of a world that had been alive. Its interior, by every rule of physics available in 1986, should have been dead. Those two facts could not both be true, and yet the pictures insisted they were. So the scientists were left holding a contradiction, and the only way out of a contradiction is to find the hidden assumption that is wrong. Somewhere in the reasoning that declared Miranda a frozen, finished ball of ice, there had to be a mistake. The face of the moon proved it. The mistake, it turned out, was in where everyone had been looking for the heat. Every source of warmth considered so far had been internal and self-contained. Heat left over from formation, heat trickling out of radioactive elements buried in the rock. Both of these are properties a world carries inside itself, and both fail for the same reason on a body as small as Miranda. There simply is not enough material to hold the warmth, and the surface is far too large to keep from bleeding it away. If those were the only options, Miranda really would be dead, and the surface really would be impossible. But they are not the only options. There is a third source of heat, and it does not come from inside a moon at all. It comes from the moon's neighbors. It comes from gravity, and it can turn a frozen world inside out. It is called tidal heating, and to understand it, you have to stop thinking of a moon as a solid, rigid ball and start thinking of it as something that can be squeezed. Gravity does not pull on a body evenly. The side of a moon facing its parent planet is closer to that planet than the far side is, and so it feels a slightly stronger pull. This difference in pull across the width of the moon stretches it very slightly into an elongated shape, drawing up a bulge on the near side and the far side both. This is exactly the same effect that raises the ocean tides on Earth, which is why it carries the name. Now, if a moon traveled around its planet in a perfect circle, always at the same distance, that tidal bulge would simply sit there, locked in place, and nothing much would happen. But moons do not always travel in perfect circles. When a moon's orbit is even slightly stretched, slightly egg-shaped, its distance from the planet changes as it goes around. Sometimes it is closer and the tidal stretch is stronger. Sometimes it is farther and the stretch relaxes. And so, once every orbit, the entire moon is flexed, pulled into a longer shape, then allowed to relax, then pulled again over and over for millions and billions of years. Here is the crucial part. Flexing a material generates heat. You can feel this yourself with something as ordinary as a paperclip. Take one and bend it back and forth, rapidly, and within a few seconds the metal at the bend grows warm to the touch. You have not held it to any fire. The warmth comes from the bending itself, from the internal friction of the material being deformed again and again. Now imagine that paperclip is an entire moon, and the bending is done not by your fingers, but by the gravity of a giant planet, and it happens on every single orbit for the age of the solar system. The friction of all that endless flexing, deep inside the moon, releases heat. Real, substantial heat, generated from the outside by the geometry of the orbit rather than from any fuel the moon carries within. A world too small to keep its birth warmth, too small to run on radioactivity, can still be heated this way, because tidal heating does not care how big the moon is. It cares how hard and how often the moon is being squeezed. This was the loophole in the argument that had declared Miranda dead. Tidal heating had been left out, and tidal heating is precisely the kind of heat source that can warm a small world from within, crack its crust, and give it the energy to remake its own surface. But there was an immediate objection, and it is a good one. Tidal heating only works if the moon's orbit stays stretched, if it keeps that slightly egg-shaped path that makes its distance vary. And left to itself, a stretched orbit does not last. The very flexing that generates the heat also drains energy from the orbit, and over time it tends to pull the orbit back toward a lazy, comfortable circle. A circular orbit means a constant distance, a constant tidal bulge, no flexing, and no heat. So even if tidal heating had warmed Miranda once, you would expect it to have switched itself off long ago as the moon's orbit rounded out. To keep the engine running, something has to keep re-stretching the orbit, actively, over and over, fighting the natural tendency toward a circle. Something has to keep pumping. That something is one of the most elegant ideas in all of planetary science, and it is called an orbital resonance. Think of pushing a child on a swing. If you shove at random moments, your pushes mostly cancel out and the swing goes nowhere in particular. But if you push in rhythm, once per swing, always at the same point in the arc, each small push adds to the last, and the swing climbs higher and higher from almost nothing. Timing is everything. A tiny force, applied in perfect rhythm, builds into a large effect. Orbital resonance is this same principle written across a planetary system. When two moons orbit the same planet with periods that fall into a simple ratio, one moon completing exactly 2 orbits for every one that its neighbor completes, say, or 3 for every 2, then the moons line up in the same relative positions again and again, at the same points in their orbits. Each time they line up, they tug on each other gravitationally. And because the tug always comes at the same rhythm, like the pushes on the swing, the little pulls do not cancel out. They add up. They pump. This is not a hypothetical. We can watch the very same machinery running today, one planet inward, at Jupiter. Its innermost large moon, Io, is locked in exactly this kind of rhythm with 2 neighboring moons, and that resonance keeps Io's orbit stretched just enough that Jupiter flexes it relentlessly on every pass. The most volcanically violent world in the entire solar system, a sulfur-yellow world in perpetual eruption, its surface torn by scores of erupting vents, some flinging plumes of sulfur and molten rock hundreds of kilometers into space. Io is not warmed by the distant sun and not running on leftover heat. It is kneaded hot from within by tides, driven by resonance with its neighbors. If gravity can do that to Io right now, then the idea that it once did something similar and gentler to Miranda stops sounding far-fetched. What they pump is exactly the thing tidal heating needs: the stretch of the orbit. A resonance between 2 moons can force one of them onto a more egg-shaped path and hold it there, or drive it there periodically, resupplying the very orbital stretch that flexing would otherwise smooth away. So resonance and tidal heating work as a pair. The resonance keeps the orbit stretched. The stretch keeps the moon flexing. The flexing keeps the moon warm. Put the two together and you have a way to heat a small, cold, distant world for a very long time, using nothing but the gravity of its neighbors and the geometry of their orbits. Now bring this back to Miranda. Miranda does not orbit Uranus alone. It is the innermost of 5 large moons, with Ariel, Umbriel, Titania, and Oberon arrayed farther out. Today, Miranda is not caught in a strong resonance with any of them. But the arrangement of orbits in a planetary system is not fixed forever. Orbits slowly migrate over billions of years, and moons can drift into a resonance, remain locked in it for a long stretch of time, and later drift out of it again. Detailed calculations of the history of the Uranian moons suggest that Miranda very likely passed through one or more such resonances with its neighbors in the past. Most often discussed is a past resonance involving Umbriel. And that while it was locked in that rhythm, its orbit would have been pumped into a pronounced stretch. During that episode, and only during that episode, Miranda would have been flexed hard by Uranus on every orbit, and tidal heating would have poured energy into its interior. This is the leading modern explanation for how so small and cold a moon could ever have come alive. And notice what a different kind of story it is from the shattered and reassembled idea. In that older picture, everything happened in a single instant of catastrophe from outside. In this one, the drama comes from within, and it comes in episodes. A moon can drift into resonance, heat up, deform its surface, and then drift out of resonance and slowly freeze again. And it can do this more than once over its history. That is enormously important because remember what Miranda's surface actually shows. Not one uniform kind of terrain, but old cratered plains sitting beside young, reworked provinces. Ancient and fresh, dead and reactivated, side by side. An engine that switches on and off, warming the moon during resonant episodes and letting it go cold between them, is exactly the kind of engine that would leave a surface like that. Some regions untouched since the beginning, others remade during a later burst of heat. So suppose the heat was there. Suppose that for some long stretch of Miranda's past, tidal flexing driven by a resonance warmed its interior. What would that heat actually do to the surface? How do you get from the inside is warm to canyons kilometers deep, towering fault scarps, and 3 enormous geometric coronae? Start with the simplest consequence. When you heat the interior of an icy world, it tends to expand, and material may rise and redistribute inside it. A crust sitting on top of a shifting, warming interior gets stretched, and ice, for all that it feels like solid rock at Miranda's brutal temperatures, cannot stretch without breaking. So it fractures. It pulls apart along faults, dropping great blocks down to make the deep canyons and raising the cliff-like scarps where the crust breaks and offsets. It cracks into the long parallel systems of ridges and troughs that lace the young terrain. This kind of tectonic extension, the stretching and faulting of a crust under stress from below, accounts naturally for much of Miranda's violent landscape. The chasms, the grooves, the great cliff of Verona Rupes described a little earlier. These are the signatures of a crust that was placed under tremendous strain and tore. That is what tidal heating does at the surface. It stresses the shell until the shell gives way. But extension and faulting alone do not explain the hardest feature of all, the one that made the coronae the central puzzle. Cracking a crust can give you fractures and canyons. It does not obviously give you 3 vast, bounded, internally banded ovoids with crisp geometric edges. For those, the leading models reach for something more dramatic, happening deeper down. Convection. Picture a lava lamp. Warm blobs of material at the bottom, heated from below, become slightly less dense than their surroundings, and begin to rise, drifting slowly upward in great rounded plumes, while cooler material sinks around them. The whole fluid organizes itself into a pattern of rising and sinking cells. Now, imagine this same slow, churning motion happening not in colored wax, but in the warm, deep ice of Miranda's interior, driven by tidal heat from below. Warm, buoyant ice would rise in broad plumes toward the surface, spreading out as it reaches the cold, rigid crust, while colder, denser material sinks back down elsewhere, where a warm plume pushes up against the underside of the crust over a broad region. It can deform that crust, wrinkle it, resurface it, and stamp it with concentric and parallel bands, the very texture the coronae display. The sharp outer boundary of a corona in this picture marks the edge of the upwelling region, the place where the rising, churning terrain gives way to the older ground that was never disturbed. This is why convection-driven models are so appealing for Miranda. They naturally produce bounded provinces with organized internal structure, formed in place, out of the moon's own material. They explain the very thing the rubble pile idea could not. The coronae stop looking like inserted foreign pieces and start looking like the surface expression of gigantic slow-motion churning cells rising from a warm interior. It would be dishonest, though, to present the rising plume picture as the settled answer, because there has been a genuine decades-long argument about which way Miranda's interior actually moved to make the coronae, and the two leading camps propose opposite motions. The upwelling camp is the one described so far, warm, buoyant material rising from below, either as broad convective cells or as discrete blobs of low-density ice pushing upward, a process geologists call diaporism, deforming the crust from beneath, driving it to stretch and fracture, and possibly feeding cryovolcanism at the surface. In this view, a corona marks a place where something rose. The downwelling camp proposes almost the reverse. Here, the corona mark places where denser, colder material sank, dragging the surface down and inward, and crumpling it into the banded provinces we see. In some versions, this sinking is tied back to the old idea of impact and reassembly, with heavy fragments settling like debris drifting to the bottom of a stirred glass of water. The distinction is not a quibble. Rising and sinking make different predictions about the topography, the fault patterns, and the internal structure of a corona, and researchers have spent years testing the observed grooves and ridges against both. And there is at least a third possibility that does not fit neatly into either camp, that the coronae, or parts of them, reflect the thickening of Miranda's ice shell as the moon cooled and partly refroze, the growing shell warping and cracking the surface as it expanded. So even at the level of the basic motion involved, up, down, or the slow swelling of a freezing crust, Miranda's coronae are not fully solved. What can be said is that the upwelling by convection picture has some notable evidence in its favor. When researchers modeled convection inside Miranda in detail, they found that a churning interior, warmed by tides, could reproduce the general distribution and deformation of the corona reasonably well, but only if the ice was soft enough to flow, which in turn demands tidal heating, because the slow trickle of radioactive warmth alone cannot make Miranda's ice mobile. In other words, the convection models only work if the resonance and flexing engine described earlier was actually running. There is also that geometric hint set up in the earlier tour of the coronae. The way Arden and Elsinore ride the moon's leading and trailing faces. That specific arrangement turns out to be close to what a simple, large-scale convective pattern inside Miranda would predict. It is the kind of quiet correspondence between model and observation that makes scientists take an idea seriously. There is one further consequence of a churning interior that is strange enough to deserve mention, because it may have literally moved the moon's geography. If a large blob of warm, low-density ice rose within Miranda, it would have made one region of the moon slightly lighter than the rest. A spinning body does not tolerate that kind of imbalance forever. Over time, it tends to reorient itself, slowly rolling so that the lighter region migrates to a new position in a process called true polar wander. Several researchers have suggested that Miranda may have undergone exactly this, that the moon physically rolled over at some point in its past, relocating its own terrain relative to its poles, driven by the buoyant upwelling within it. A similar reorientation has been proposed for other icy moons. If it happened, it means Miranda's face is not merely fractured and resurfaced, but rearranged. The map was redrawn from inside, and features may not sit where they first formed. Underlying all of these debates is a deeper uncertainty about Miranda's very structure. Specifically, how thoroughly it ever separated its rock from its ice. A world that fully sorted itself, with dense rock sinking to form a core and lighter ice floating above, behaves very differently under tidal flexing than a world that stayed a more uniform mixture. How completely Miranda differentiated in this way is not known, and it strongly affects how much tidal heat the moon could generate and where. That single unknown ripples through everything: the depth of any ocean, the vigor of convection, the height a fault can reach, even whether the moon could roll over. All of them depend on how Miranda's rock and ice are arranged inside, and that arrangement is something no flyby could ever measure. There is even a way to estimate how warm Miranda's interior once was, written into the faults themselves. The depth to which a brittle crust can break before the material below becomes too warm and soft to hold a fault is set partly by how much heat is flowing up from within. When researchers examined the geometry of Miranda's great fault scarps, the very cliffs and canyons described earlier, including the towering scarp of Verona Rupes, the fracturing implied surprisingly high heat flow in places, especially near the coronae. That is independent support for the central claim of this whole story, that at some point, this small frozen moon was not cold at all on the inside. It was warm enough to crack deeply, flow slowly, and remake its own face. Exactly the condition the resonance and tides engine is meant to explain. None of this erases the disagreements. The upwelling and downwelling camps still argue. The degree of Miranda's internal sorting is still uncertain. Whether the moon rolled over is still unproven. But notice that every one of these competing ideas now takes for granted the thing that seemed impossible at the start. That Miranda had real internal heat to work with. The debate is no longer whether the moon had an engine. It is only about exactly how that engine drove the machinery at the surface. And there may be an even more active ingredient in the mix: cryovolcanism. On a warm, rocky world, molten rock rises and erupts as lava. On a cold, icy world, the equivalent would be warm, soft, mobile ice, slush, or briny liquid water welling up from below and spreading across the surface before refreezing. This is cryovolcanism, ice volcanism, and it is not a fantasy. It has been observed or strongly inferred on several icy bodies elsewhere in the solar system. If Miranda's tidal heating warmed its interior enough to mobilize its ice this way, then upwelling slush could have flooded across regions of the surface, burying and erasing the old craters, resetting that patch of ground to a young, fresh state. That is precisely the resurfacing needed to explain the crater-poor young terrain sitting beside the crater-corroded ancient plains. It is worth stressing that the exact role of cryovolcanism on Miranda remains uncertain and debated. It is a plausible contributor, not an established fact, but it fits the pattern of a moon that reworked whole provinces of its surface during episodes of internal warmth. Put all of this together and a coherent, natural, and genuinely extraordinary picture emerges. One that requires no catastrophe from outside at all. Miranda drifts into a resonance with a neighbouring moon. The resonance pumps its orbit into a stretch. The stretch drives relentless tidal flexing. The flexing heats the interior. The warm interior convects, rising in great plumes that deform the crust into coronae, while the stressed shell fractures into canyons and scarps, and mobilized ice resurfaces whole regions. Then, eventually, Miranda drifts out of resonance. The pumping stops, the orbit rounds toward a circle, the flexing fades, the interior cools, and the moon freezes once more, until perhaps it happens all over again in a later episode. The moon that looked rebuilt was, in this telling, a moon that repeatedly rebuilt itself from within, powered by the gravity of its neighbors. It did not need to be shattered. It only needed to be squeezed. And then, in 2024, a new study pushed this picture further than many scientists expected it could go, and turned Miranda from a merely reactivated moon into a candidate ocean world. A team led by Caleb Strom, a graduate student at the University of North Dakota, working with the planetary scientist Tom Nordheim of the Johns Hopkins Applied Physics Laboratory, and Alex Patoff of the Planetary Science Institute, went back to the same decades-old Voyager 2 images that had launched the whole mystery, and read them backward. Rather than starting from a theory of Miranda's interior and predicting what the surface should look like, they started from the surface we can actually see and asked what interior could have produced it. They carefully mapped the moon's observed fractures, ridges, and the boundaries of its coronae, and then they built computer models of many different possible internal structures, calculating in each case the pattern of stresses that structure would have imposed on the crust. Then they compared those predicted stress patterns to the real map of cracks and features. The question was simple. Which interior, when flexed by tides, would break the crust in the pattern we observe? The answer was a surprise. The internal structure that best reproduced Miranda's fractured, ridged, corona-marked surface was not a solid ball of ice. It was a moon with a liquid water ocean beneath its crust. According to their results, published in the Planetary Science Journal in October of 2024, Miranda likely harbored a subsurface ocean sometime in the relatively recent past, roughly 100 to 500 million years ago, and it was not a thin film. The best-fitting ocean was at least about 100 kilometers deep, lying beneath an icy shell no more than about 30 kilometers thick. Given that Miranda's radius is only about 235 kilometers, an ocean of that depth would have filled very nearly half of the entire moon. A world barely 1/7 the width of our own moon, adrift in the frozen dark 2 billion miles from the sun, may once have been, beneath its shell, close to half liquid water. It is essential to be clear about what kind of claim this is, because the distinction runs through this whole story. This is not a confirmed, directly observed fact. No instrument has ever detected an ocean inside Miranda. It is the output of a model, a leading, well-motivated, carefully constructed model that reverse engineers the interior from the surface. And it stands as a candidate discovery, a strong and provocative hypothesis rather than a settled truth. The team themselves framed it in those terms, noting how surprising it was to find evidence pointing toward an ocean inside so small an object. What gives the result its weight is that it flows naturally from the same machinery already discussed. A past resonance drives tidal heating, and the researchers found that the heating needed to crack Miranda's crust, the way we see it cracked, is the kind of heating that would also melt a substantial ocean beneath the shell. The ocean is not an extra exotic add-on. It falls out of the very same explanation that accounts for the corona and the canyons. And Miranda is not alone in raising this possibility among the moons of Uranus. In the same period, other researchers examining Oriole, the next moon out, and one whose surface also shows signs of past resurfacing and tectonic activity, have found hints from telescope observations of the carbon dioxide ice on its surface that it too may hide a subsurface ocean-feeding material up from below. Taken together, these results have begun to reshape how scientists think about the entire Uranian system. Instead of a giant planet attended by a set of inert frozen snowballs, Uranus may preside over a family of moons in which more than one is, or recently was, an ocean world. That reframing is part of why interest in returning to Uranus has intensified. But the ocean models, for all their appeal, are built on a thin foundation, and honesty demands that we look squarely at what they still cannot do. They cannot yet pin down the timing. The estimate that Miranda's ocean existed 100 to 500 million years ago is a broad window, and whether any liquid water survives beneath the shell today, in some diminished form, or whether it long ago frozen solid, is genuinely unknown. They struggle too with the deepest question of all: why Miranda? Its neighbours formed from similar material, in the same system, subject to the same kinds of resonances and tides. And while Ariel shows its own signs of past activity, none of the large Uranian moons wears its history as violently on its face as Miranda does. Why this small moon should have been so thoroughly and repeatedly transformed when worlds larger and seemingly better placed to hold heat were not, remains unresolved. And even the convection models that reproduce the corona so appealingly do not reproduce every detail of their exact shapes, orientations, and internal patterns. They capture the character of the coronae without perfectly matching all three of them, feature for feature. The leading explanations are far more credible than the old shattered moon idea, and they hang together in a way that idea never quite did. But more credible is not confirmed, and Miranda is a moon that has humbled confident predictions before. There is one more limitation, and it is the one that quietly undermines everything else, no matter which model you favor. Every theory described so far, the resonance, the tidal heating, the convection, the cryovolcanism, and now the ocean itself, has been built, tested, and argued over using essentially one afternoon's worth of images of roughly half of one small moon, taken in a hurry, at modest resolution, from tens of thousands of kilometers away, nearly 4 decades ago. The 2024 ocean study did not draw on some rich new dataset. It went back to the very same Voyager 2 pictures and squeezed them harder. The entire towering structure of modern thinking about Miranda's violent inner life rests on a fraction of the evidence a single spacecraft happened to gather during a few hours in 1986 on the lit half of a world whose other half no human eye has ever seen clearly at all. Which means the most important question about Miranda may not be which model is right. It may be what is still hidden on the unseen hemisphere beneath the ice, and in the details too fine for a 40-year-old glimpse to resolve. And that is exactly where the story has been heading all along. When Voyager 2 swept through the Uranian system on the 24th of January, 1986, the sideways geometry of the planet meant the sun was pouring down on Miranda's southern hemisphere, while the northern hemisphere lay buried in a decades-long polar night. The cameras could only photograph what was lit, and only from the angles a single fast pass allowed. So roughly half of Miranda has never been seen in any real detail at all. It rolled beneath the spacecraft cloaked in darkness, and it has stayed dark to us ever since. Nearly 40 years later, there's an entire hemisphere of this moon that no human eye and no human instrument has ever resolved. It's the letter that arrived, was set on the table, and was never opened. Try to sit with how strange that is. We have built an elaborate scientific understanding of one of the most bizarre objects in the solar system. We argue about its interior, we model its oceans, we reconstruct its history across billions of years, and we have done all of it while looking at half the evidence. It is a little like being handed a single torn page from the middle of a book and being asked to reconstruct the entire plot. The beginning, the ending, the motivations of every character, the meaning of the whole. You can make real progress. A clever reader can infer a great deal from one page, but you would be a fool to mistake your reconstruction for the book itself, and you would be wise to expect that the missing pages hold surprises. Miranda is that book. We are working from the one page that happened to be lit. And yet, even from that one page, something undeniable can be read. This is where we can finally say plainly what this whole story has been circling, and where the mystery finally comes clean. Miranda looks like it was rebuilt, but it almost certainly was not, in the literal sense, ever shattered and reassembled. That old dramatic idea, a moon blasted apart and gravitationally glued back together, was a reasonable first guess in the shock of 1986. And it captured the raw emotional truth of those first images better than any careful phrase could. But the more closely scientists looked, the less the surface behaved like frozen wreckage, and the more it behaved like something worked from within. The coronae are not the tops of sunken fragments. They are not seams where foreign pieces were joined. They are the surface expressions of Miranda's own interior in motion. Provinces raised, banded, and bounded by forces rising out of the moon itself. The appearance of the assembly is completely real. The assembly never happened. So what does rebuilt actually mean once you strip away the catastrophe? It means something stranger and, in its way, more disturbing than a simple collision ever could be. It means that this small, frozen, distant moon appears to have remade its own surface, not once in a single event, but apparently in more than one episode across its long history. It fractured. It stretched. It heated from the inside. It resurfaced whole regions, erasing their craters and resetting their clocks, while leaving other regions untouched since nearly the beginning. And then, most likely, it went cold and quiet, only to stir again later. The reason Miranda looks like a patchwork of several different worlds is that, in a sense, it is a record of several different Mirandas. The moon at different stages of its own life, preserved side by side on a single body. That is the deepest way to understand this world, and it is worth dwelling on because it is genuinely rare. Most surfaces in the solar system tell one dominant story. The ancient lunar highlands tell the story of relentless bombardment and nothing else. A fresh, smooth ice plain tells the story of one great resurfacing, but Miranda refuses to settle on a single narrative. Its face is like a medieval manuscript in which a scribe wrote a text. Then, centuries later, another scribe scraped part of the page clean and wrote over it, leaving both the old faded writing and the new ink visible together on the same sheet. Examine one region and you are looking at Miranda's most ancient chapter. The cratered plains that have collected impacts since the dawn of the system. Examine the region beside it, across a knife-edge border, and you are looking at a much later chapter, terrain reworked long after the moon formed. The eras do not blend. They abut. They sit on top of one another and beside one another, several distinct ages of one world crowded into a single small ball of ice. It is like standing in one of those ancient cities where each generation built directly on the ruins of the last, so that a single excavation cuts down through a modern street, a medieval wall, a classical temple, and a prehistoric hearth, all stacked in one place. To dig is to move through time. Miranda is that kind of place, except its layers are not stacked neatly by depth. They are laid out beside each other on the surface, exposed all at once, so that a single glance takes in eras separated by billions of years. That is why it looks unreal. Your eye expects one world, one moment, one story. It receives many, jammed together, with the seams showing. And here's the reflection that Miranda pushes on anyone who looks at it long enough. We tend to assume that the small, cold, out-of-the-way worlds are the boring ones. The drama belongs to the big planets, the warm places, the objects near the sun. The whole confident prediction before the flyby was built on that assumption. Too small, too cold, too far, therefore dead, therefore dull. Miranda broke that assumption in a single afternoon. It showed that a world does not need to be large, or warm, or close, or important looking to have lived a violent life. It only needs the right circumstances. A neighbour to lock rhythms with, an orbit that can be stretched, a giant planet to squeeze it, and even a frozen runt at the edge of the known solar system can crack itself open, warm itself from within, and rebuild its own face. The capacity for a dramatic history, it turns out, is not reserved for the grand objects. It can hide inside the smallest and most overlooked. That is a genuinely humbling idea, and Miranda is its clearest teacher. But, and this matters just as much as everything before it, none of this means the case is closed. It is easy in telling a story like this to let the modern explanation sound like a solved problem, to let tidal heating and resonance and the possible ocean line up so neatly that the mystery seems finished. It is not finished. The honest state of things is that we have a set of plausible, well-motivated, mutually reinforcing ideas that are far more credible than the old shattered moon hypothesis, and that hang together in a way that idea never did. And we still do not know the exact sequence of events that produced the moon we see. Consider everything that remains genuinely unresolved. We do not know precisely when Miranda's episodes of heating occurred, or how many there were, or how long each lasted. The estimate that a subsurface ocean existed something like 100 to 500 million years ago is a broad window, and whether any liquid survives beneath the shell today or froze solid long ago is simply unknown. We do not fully understand why Miranda, of all the Uranian moons, wears its history so violently. Its neighbours formed from similar material in the same system, subject to the same kinds of gravitational rhythms, And while Uriel shows its own signs of past activity and possible ocean, none of the larger moons is scarred the way this smallest one is. Why the runt should have been the one so thoroughly transformed is a real and open puzzle. Even the elegant convection models that reproduce the character of the corona so well do not perfectly reproduce all three of them, feature for feature, in their exact shapes and orientations. And every one of these questions is being wrestled with using that same 40-year-old glimpse of half a moon. The models are strong. The data beneath them is thin. That combination should make anyone cautious about declaring victory. So Miranda leaves us in a peculiar and rather beautiful position. We understand it far better than we did in 1986. We have moved from a catastrophe smashed it to its own interior remade it, which is a real advance in understanding, not a retreat into mystery. And at the same time, we are acutely aware that the whole edifice is built on one page of a much longer book, and that the missing pages, the unseen hemisphere, the fine details our old images cannot resolve, the interior we have never directly probed, could confirm the picture, complicate it, or overturn it entirely. Both of those things are true at once. We know more than ever, and we know how little that more really is. Which raises the obvious question. If the entire mystery hinges on the fact that we have only ever seen Miranda once, briefly and in part, then why not go back? For a long time, that question had no realistic answer. Uranus is monstrously far away, and reaching it is genuinely hard. But in recent years, going back has moved from a wish to a formal priority. When the planetary science community in the United States conducted its most recent decadal survey, the once-a-decade exercise in which the field collectively decides what matters most for the coming years, it named as its single highest priority new flagship class mission a return to Uranus. The concept is called the Uranus Orbiter and Probe. Unlike Voyager 2, which could only fly past and wave goodbye, this mission is designed to enter orbit around Uranus and stay, spending years touring the system. Its baseline plan includes a science phase of roughly 4.5 years, during which it would make repeated close flybys of all 5 of the major moons, Miranda among them, while also dropping a probe into the atmosphere of Uranus itself to sample the planet directly. It is, in essence, the mission built to answer exactly the questions this story has raised. Think about what such a mission could do for Miranda specifically. It could image the moon at resolutions far beyond anything Voyager 2 managed, turning our blurry, decades-old glimpse into a sharp, modern map. It could, given the right timing and geometry, photograph the hemisphere that has spent 40 years in darkness, finally opening the sealed letter, finally reading the torn-out pages. It could measure Miranda's gravity field precisely enough to probe whether there is, even now, a layer of liquid water hidden beneath the ice, testing the 2024 ocean model against direct measurement rather than inference from old pictures. It could study the exact structure of the coronae up close, checking the convection models against reality, and it could look for signs of recent or ongoing activity that would tell us whether Miranda's engine is truly dead or merely sleeping. Nearly every competing idea we have walked through makes different, testable predictions about what a closer look would reveal. A real orbiter lingering in the system could finally start ruling ideas in and out instead of endlessly rereading the same 40-year-old frames. it is worth being concrete about what a returning spacecraft could actually test, because these competing ideas are not vague hunches. Each one predicts something specific that a well-equipped orbiter could go and check. Take the question of whether Miranda still holds liquid water today. There is a clever way to look for a hidden ocean without ever drilling, and it has already worked at other moons. A subsurface ocean, if it is salty, conducts electricity. When such a moon is bathed in the changing magnetic field of its parent planet, that conductive layer responds by generating a faint magnetic field of its own. The buried ocean, in effect, gives itself away. Detecting that induced signal is one of the main ways scientists inferred oceans inside the icy moons of Jupiter, and an orbiter carrying the right instruments, making repeated close passes of Miranda, could look for exactly the same telltale reply. A clear answer would turn the 2024 ocean model from a candidate into either a confirmed feature or a discarded one. The rival models of the coronae make their own testable predictions. High-resolution imaging and precise measurements of the shape of the land, whether a corona bulges upward or sags downward, how its faults are arranged, how its interior is structured, could help settle whether these provinces were raised by rising warm material or pulled down by sinking cold material. The central disagreement from before, detailed thermal and gravity measurements could map where heat once flowed, and how mass is distributed inside the moon, and simply photographing the unseen northern hemisphere would test the idea that Miranda rolled over in its past. If the global network of rifts and the pattern of the corona continue across the terminator into the dark half in a way that matches the reorientation models, that would be powerful evidence that the moon really did rearrange its own geography from within. There is a larger reason all of this matters beyond Miranda itself, and it is worth stating carefully to avoid overreaching. The researchers behind the ocean model have been explicit that their work is not a claim that anything lives on Miranda. What it offers instead is a case study in what it takes for a small, cold, icy moon to become an ocean world at all. What combination of size, orbit, resonance, and tidal heating can put and keep liquid water beneath an icy shell far from the sun? That question reaches well past one moon. Uranus may host more than one possible ocean world among its satellites, Miranda the most extreme of them. And ocean worlds are, as far as we know, among the more plausible places to look for habitable conditions beyond Earth. So, understanding whether and how a body as unlikely as Miranda could have held an ocean feeds directly into one of the largest questions in planetary science. Not whether Miranda is inhabited, which no one is claiming, but what the true requirements for a habitable icy moon actually are. Miranda, precisely because it is so small and so improbable a candidate, is an unusually demanding test of those requirements. None of these measurements would come from Miranda alone, and that is part of the appeal. A single flagship orbiter at Uranus would be the first spacecraft ever to orbit an ice giant, something no mission has done. And while it studied Miranda, it would also be studying the whole family together, gathering the comparative picture that a lone flyby could never provide. Why did Miranda, the smallest, end up the most violently reworked, while its larger siblings did not? That question can only really be answered by examining all of them with the same instruments, in the same era, and holding the results side by side. The atmospheric probe, meanwhile, plunging into Uranus itself, would read the planet's deep composition, a record of how the entire system formed, and therefore of the raw materials Miranda was built from in the first place. The moon's mystery is, in the end, entangled with the mystery of the planet it circles. There is at least a reason for cautious optimism buried in the process itself. When the planetary science community places a mission at the very top of its once-a-decade priority list, that recommendation has historically carried real weight. The two flagship missions ranked highest in the previous such survey: a spacecraft to Jupiter's moon Europa and an effort to return samples from Mars. Both moved from paper into reality in the years that followed. The Uranus orbiter and probe now sits in that same top position, judged by its own designers to require no new technological miracles, only the will and the funding to begin. That is no guarantee, but it means the mission is not a fantasy. It is a plan waiting on a decision. And there is something quietly moving about the timescale, even in the best case. If such a mission launched in the coming years and then spent well over a decade in transit, the first genuinely new close-up images of Miranda might not reach Earth until sometime in the 2040s, very nearly 60 years after Voyager 2's brief single afternoon there. A scientist who was a graduate student poring over those grainy 1986 frames could spend an entire career on this moon and only glimpse the answer near the very end of it. Whole working lives, in other words, may be spent studying half a moon in the patient faith that the rest is still out there, waiting to be read. All of that, though, still waits on a spacecraft that has not yet been built, and the road to building it is where hope meets arithmetic. But it would be dishonest to describe this mission as though it were already on its way, because it is not, and the road to it is genuinely uncertain. The original vision imagined launching in the early 2030s, using the gravity of Jupiter as a slingshot to shorten the enormous journey, with arrival at Uranus somewhere around the mid-2040s. More recent assessments have been sobering. Analyses of the mission's status have concluded that the funding needed to make an early 2030s launch simply has not materialized, which means the ideal Jupiter slingshot window may be missed, and a realistic launch has slipped toward the middle or later part of the 2030s. Engineers have been studying clever ways to claw back some of the lost time, new heavy lift rockets, and techniques like using the planet's own atmosphere to help break the spacecraft into orbit. But none of that changes the basic arithmetic of a mission that, even under good conditions, would take well over a decade in flight. The estimated cost runs to several $billion, and like all such missions, it must survive years of budget decisions before it can ever leave the ground. And there is a deadline of a kind, imposed not by politics but by orbital mechanics. Because Uranus lies on its side and takes about 84 years to circle the Sun, the geometry of the system, which hemisphere is lit, how the moons are arranged relative to an incoming spacecraft, changes slowly across decades. And some arrival windows are far better than others for studying the moons and the planet's structure. Miss the favorable configurations of the coming decades, and the truly ideal opportunity to observe the system in a particular state may not return until near the year 2091. That is not a date most people planning today's missions expect to see. It lends a quiet urgency to the whole endeavor. The best chance in generations to finally understand Miranda is real. And it is also fragile. And it is competing against the ordinary gravity of budgets and priorities that has grounded good ideas before. So we are left, for now, exactly where the evidence leaves us. with a set of powerful explanations and an incomplete view, waiting on a mission that may or may not fly in time to answer the questions in any of our lifetimes. And that suspended state is, in the end, the truest portrait of Miranda. Not a solved case, not an unsolvable one. A world we have seen just enough of to be certain it is extraordinary, and not nearly enough of to be certain how. Let me gather the whole story into its final shape. Because after everything, it comes down to something that can be said cleanly. Miranda does not need to have been literally shattered and reconstructed to be one of the strangest moons in the solar system. That was never the point, and it was never really the truth. What makes Miranda disturbing is not a single ancient catastrophe. It is that a world this small, a frozen ball of ice and rock, barely a few hundred kilometers across, adrift at the cold outer edge of the planets, appears to have been fractured, heated, stretched, and resurfaced, apparently more than once, across its history. It carries old cratered plains and young reworked provinces side by side. It carries 3 vast geometric coronae with crisp, ordered interiors. It carries canyons plunging kilometers into the dark, and a cliff so tall we still argue about its height. And it carries all of it not as the scar of one bad day, but as a layered record of several geological eras preserved together on one impossibly small body. Miranda looks like it was rebuilt because, in the most literal and astonishing sense the evidence supports, it may have repeatedly rebuilt its own surface from within. Squeezed alive by the gravity of its neighbors, warmed by its own flexing, churned and cracked and resurfaced by its own restless interior, again and again, before falling cold and still. And yet the exact sequence of that self-rebuilding, how many times it happened, precisely when, in what order, and whether a hidden ocean still lingers beneath the ice today, remains genuinely unresolved. We have a leading story, not a final one. Which brings us at the very last to the single strangest thing about this whole moon. It is not the coronae. It is not the cliff. It is not even the possibility of an ocean where none should exist. The strangest thing about Miranda is how much of its story is still missing. Everything we believe about this world, every model and every argument, was built from a few hours spent looking at half of it, once, nearly 4 decades ago. An entire hemisphere has never been seen. The interior has never been touched. The finest details lie beyond the reach of our aging images. We have been reading one lit page and calling it the book. And somewhere out there, tipped on its side in the dark, 2 billion miles away, the rest of Miranda is still waiting. A whole unseen half of a moon that already broke every rule we thought we understood. When we finally see it clearly, that unseen ground may hand us the last pieces we need to solve Miranda at last. Or it may show us something we cannot explain at all, and make this small, broken, rebuilt world look more impossible than it already does. We will not know which until we go back and open the letter. And until we do, Miranda keeps its oldest secret exactly where it has kept it all along. On the side of itself, it has never once turned toward the light.